Integration actually works a lot the same. Now, if we remember, I'm going to cover series while talking about how integration works, because integration is really just a summation, and so is derivation. So integration is a summation of a bunch of rectangles added together, right? So you have n amount of rectangles that define some function. And this is a little more in depth than I usually go, but it's a good way to think about both integration and series at the same time. So as I decrease the width of these, so if I have a delta x here, and as my delta x goes to 0, these rectangles are going to more closely approximate my curve, right? And another way to think about that is if I increase the amount of rectangles, I'm naturally going to squish them. So we're naturally going to make them smaller. So if I increase my number of rectangles, I'll more and more appropriately approximate the series. So you have two ways to think about your approximation here. You have your series approximation, and then you have integration. But both of them work kind of the same way, by adding a bunch of stuff together. The reason that's important is because integration is also linear. So I'm going to write that as well. So what that means is when we have an integration of some function plus another function, that we can distribute this integral across, right? So we get the integral of f of x dx plus the integral of g of x dx. Oh yeah. Yeah, I know all the mechanicals in the tutoring center are always stressing out about all that stuff. I'm thankful I don't have to take those classes. I should deal with electricity instead. Okay. So the other piece of linear that's important is if we have the integral of some constant times a function. That constant, just like we expect, comes right out. So those are the properties that are directly affected by it being linear. What we also need to know is integration has some other things we have to deal with. Because it's an approximation of a function, we also need to think about bounds, or in the case of an indefinite, you're going to get a constant at the end, your plus c, as we all know. So let's think about these bounds for a second, though, because let's say I have even bounds, so, or symmetrical bounds, I should say. So bounds from negative a to a, right? And I have some function that's even in this case of x. So to think about that a little more, let's consider sine. Or wait, sorry, cosine. Ha, I'm doing even first, not odd first. Okay. So I'll draw that in the middle so it makes more sense. So cosine looks kind of something like that. And so we can see if my drawing was better, it would be nice and symmetrical about the y-axis. So if we notice here, if I'm going from, for example, this is negative a, and this is a, this area here between the curve and the x-axis on this side should be the exact same as this area here. So in that case, what we can do is we can actually just say that this equals 2 times the integral from 0 to a of f even of x, which is really nice. Cuts our work in half, especially like our friend mentioned when you're doing the Fourier. Let's see. Doesn't matter what. Okay, that kind of makes sense because like at the end of multivariable calculus, you do the parameterization into the u and v domain. And they literally said, yeah, it doesn't matter, you just make it easier for yourself. So, and I know in math and signals and systems, we transfer from the time domain into the frequency domain for the same reason. So that makes sense. Crossing through. I'm sure that those are very related, and I'd be curious to see what those actually look like. I'll have to look that up later. Thank you for the tip. Okay, we're on odd now. So if we have a symmetrical integral of odd, we actually see something even more interesting that makes our life significantly easier, especially in regards to the Fourier series. So this is even, which is cosine, right? And it works for any even function. And then let's say we have an odd function like sine, right? Well, now this area is the exact same as this area, except this one's negative and this one's positive. So if I had negative capital A, and I was going to add that to positive A, well, A minus A is just 0, right? So these areas actually offset, and your symmetric integral for an odd function is just 0, right? And that makes our Fourier series really a lot simpler when we remember that, and it's also just good to know in general. Okay. Have a couple examples of these guys. So there's a couple of techniques that we'll also go into here in a minute, but we'll just do a couple of real quick base integrals just to kind of see them. Because integration is the exact opposite of derivation, I don't really feel the need to write these down explicitly. So we'll just do a couple of examples real quick and see how it goes. Okay, so the first one I've got is real simple. So we've got the integral, indefinite integral, no bounds, of sine of 2x dx. So what we're going to do here is kind of our reverse chain rule. So you can also use u substitution, which we'll talk about here in a second. But the easiest way to do this one is just to think, okay, well, let's take the integral of sine, which we know when we're going across the bound, so we're crossing from sine back into cosine, we have to get a negative going on. So we get negative cosine. And then the inside always stays the same. We know that that's always going to be true. But if I take the derivative of this, I know the chain rule is going to give me a 2. So in order to offset that, I need to divide by the derivative of the inside, basically. It's the easiest way to think about how that's going to end up working. And because this is indefinite, we need to account for the fact that it could be added to any constant and still be the same derivative, right? Because if we take the derivative of this constant, it just becomes 0. Nice and easy. Just do one more of these and then we'll learn a couple more techniques and see how it works out. Okay, this next one is going to be the integral from -1 to 1 of 4x to the -4 divided by 3x to the -2 times x squared dx. So you could just go straight into taking the derivative of this, but I really wouldn't recommend it, especially when you stop for a second and look at this and say, okay, what is this actually going to do? So if we flip this x to the -2 up into this guy, we get x to the 4th. So we're going to pull out this 4/3, 4 over 3, then integral. And so now we have x to the -4 and x to the 4. Well, we know that we have the same base here, so we can add these together. So we actually just get 4 over 3 and the integral of x to 0 dx, which is going to be equal to 4 over 3 and the integral. I guess I should be a little more careful about my bounds. So this x to 0 becomes 1 dx. Now, it may be tempting to say, well, that doesn't matter at all. It does still matter. In our case, though, you could use a simplification here because 1 is an even function. So you could multiply it by 2 and just take half of it, which we'll do just for good practice, but isn't really necessary in this case. So we'll have 4 over 3 times 2 integral 0 to 1 of 1 dx. Okay? And so this becomes, of course, 8 over 3 out here. And then the integral of 1 is just going to be x, because you go up a power, right? And so then we're just going to have x evaluated from 1 to 0. And then that's going to equal 8 over 3 times 1 minus 0, which is just 8 over 3. Okay, so we're going to start with u substitution, but they kind of both go together in the same general form. So for u substitution, we always have to deal with these inside functions in some way that makes our life easier. So in the context where we have an outside function, which, for example, we'll just say, I don't know, we'll just say cosine of x squared, right? And let's say we have two functions multiplied by each other is what I need. Yeah, that's what I need. Okay, I need to write this correctly. That would help. So if we have f of g of x times g prime of x, that's what we want. We can use u sub. Okay? So in this case, we have here where the inside function of this cosine is the parent function, or the integrated function of this outside function. Or the other way to say that is this outside function is the derivative of the inside. So in this case, we can actually go ahead and let some substitution variable, which we'll call u, equal the inside function. And then the outside function we will get when we take the derivative of this u function. So the derivative of this x squared becomes 2x dx. And now we have to be really careful here because we want to make sure that we are correctly substituting all of the x's here. So we have this x is being substituted by u, and then we have this x and the dx are getting substituted by du. Now a little problem though, we don't have this 2 here, so we have to make sure to rectify that. So we're going to actually divide the 2 over, and now we have x dx by itself. Nice and easy. So now we plug in our substitution, and we're going to get the cosine of u, and then we have du over 2 is multiplied. Now this 1 over 2 is just constant, so we can pull that out. So we have 1 over 2, and then integral of cosine of u du is just going to be the integral of cosine we already know, which we're going cosine to sine, so we can keep our sign the same, so we get sine of u. And then there's always your plus c. Now in this case, this is an indefinite integral, so we definitely have to plug back in our original function. So we get 1 over 2 sine of x squared plus c. And now if we were to take the derivative of this after doing our chain rule, we would get our original function again. What's important to note is we didn't have bounds on this one, so it's not really super complicated. We just plug back in our original function. But if we did have bounds, we have 2 options. And we'll do one of those examples here in just a second. But when we do our substitution, we can change our bounds from our x domain to our u domain, or we can leave the bounds in the x domain, but we have to plug back in our x's first, and then we can plug in our bounds. So let's look at an example of that. Hopefully I have one pulled up already. Here we go, u sub, that's what I want. Okay. So I have, yeah, great. Okay, so let's do the integral of -1 to 2 of x, and then sine of x squared, pretty similar, dx. Okay, so this will be pretty similar to what we just did. So in this case, we're going to do the same substitution because nothing really changed there. So we're going to let u equal this x squared. We'll take our derivatives. We get du is equal to 2x dx. Now we still don't have the constant 2 up here, so we're going to divide across by 2 again. And so we get du over 2 is equal to x dx. Now the problem is, this is x equals 2 and x equals -1. So sometimes it's easier to change your bounds and just leave it that way. Sometimes it's easier to leave them in their original and plug back in your original function. It just depends. Yeah, I do believe you're correct that that u sub is the one-dimensional Jacobian, because integration by parts is the two-dimensional, and then surface integration you have to do a three-dimensional, depending on if you're going over a three-dimensional volume. Yeah, I think you're right. Okay, so let's go ahead and change our bounds just for good practice, because it's not something we do super often in earlier versions of calculus, but you're going to do it all the time in Calc 3. So we're just going to literally plug in these original values into our u here. So let's say that u is equal to 2 squared, which is 4. And then we have our other u is -1 squared, which is 1. So in our new integral, our lower bound is 1, and our upper bound is 4. And now we can write our new integral, which is the sine of x squared, and then times du over 2, right? Because we were able to substitute all of our x's. So this substituted nice and clean here, and then this substituted here. Okay? And then this integral works out very similarly to the last one. So the 1/2 can just come out. Now the integral of sine is going back over the hump to cosine, so we do get a negative in this case. So we get negative cosine of x squared. Or sorry, this should be u. I apologize. I got distracted. This is negative cosine of u. And then that's evaluated from 1 to 4. Now 1 to 4 are not great evaluation bounds for a cosine function or sine function, but neither are negative 1 and 2. So we're equally in trouble either way in this particular case. So in our case we'll have, I'll get to what you said in a second. So negative 1 over 2 times cosine of 4 minus cosine of 1. And then you could distribute the negative, which just flips these, but there's not really a need to. And without a calculator, that's as far as we can go on this problem. So integration by parts is what we do when we can't really do a u substitution because you don't have a function where one is the derivative of part of the other, but you do have two functions together. So this is easier just to show as an example. So if we have, for example, x squared and the cosine of x dx, well, this might initially look to the untrained eye like you might be able to use sub, well, what if I let u equal x squared? Well, if you let u equal x squared, you're going to get the du inside, which means you can't cancel your dx, and that just doesn't work. So unfortunately, in this scenario, that option isn't really going to happen for us. So we have this other technique we can use, where we're going to select part of the function to be a u, and the other part of the function to be a dv. And what we're going to do is we're going to take the derivative of the u, and we're going to take the integral of the dv. So what we're going to do here is this is kind of the breakdown of how we're going to split this up into something we can deal with, and then we're going to plug it into a formula where we have u times v minus the integral of v times du. And now this is the long way to do it. For anything other than the times, you only need to do it twice, and even then it's almost always faster to do what's called the tabular method, which we'll get into. But for this case, let's just go ahead and do it this way. Now the thing we have to think about is how do we choose which one's which? So you always want to choose your u to be something that when you're taking derivatives is going to get to 0 when possible. Or if it's not possible, in the case of like e to the x times cosine of x, you want to do the u to be one that's going to cycle back to what the original was, so you can use a different technique, which we'll go over as well. But to start, let's deal with this guy as we have it written. So something that's going to go to 0 eventually as we take derivatives. Well, cosine just turns to sine, which turns to cosine, which turns to sine, which turns to cosine, which turns to sine. So that's not going to go to 0. But x squared is, because x squared turns to x, turns to 1, turns to 0. So let's do x squared. And so that means our other piece has to be this cosine of x dx. Yeah, if you want to toss in that equation, I'll look at it as soon as I'm done working through this example. Okay, so let's take our derivative here. So du is going to be equal to 2x dx, and then dv integrated is becoming v, which is now the integral of cosine of x dx, which is just going to be sine, right? Sine of x. Now we plug everything into our formula, so we get x squared sine of x, and then minus integral v is sine, and then du is this 2x dx. Okay? Well, so we see here, we're going to have to do it again, right? So let's choose our u. We want to be consistent and choose the same u's. The only thing that I'm going to do a little differently is I'm going to pull this 2 out first. So I'm just going to take the x. I don't need to take 2x, right? And then our dv will just be our sine of x. And then here we have du is equal to 1 dx, and then v is going to be the integral of sine, which when we're going back over the hump, so it becomes negative cosine, right? So now we rewrite this. We get our x squared and sine of x stays just as it was. And then you have to be really careful when doing the formula way to track your parentheses. It's really easy to get lost here. So we have our negative here around everything that comes after this, right? Because this formula is coming after all of this point. And now we're going to do the same formula again. So we get u and v. So we get negative x cosine of x, and then minus the integral of v du. So v is this negative cosine, and du is just dx. So minus integral negative cosine of x dx. So we got a lot of negatives. So let's simplify some of those and do our last integral, which is now just a clean straight integral. So we have x squared sine of x. I'm going to distribute this negative across. So negative and negative is positive. And then negative and negative is positive, but this negative comes out as well, so that's still negative. So we have negative integral cosine x dx. Okay? And then all I have to do now is take the integral of this last piece. So we get x squared sine of x plus x cosine of x. And then the integral of cosine is just straight to sine. We're not going over the hump, so we're good. We can just keep it positive, which in this case is negative. So we just get sine of x. And then this is an indefinite integral. So this is plus c. Easy thing to forget and lose points on, so you want to be very careful. And while you're still typing up that equation, since it looks like you're still probably typing, I'm going to also show the tabular method to do this so we can see how much faster that is. So all we have to do here is make 3 columns. And in this plus minus column, you just start positive, negative, positive, negative. Your derivative is what you're choosing as your u. So it's the thing that's going to go to 0, hopefully. So in our case, we chose x squared from our original. And then our integral is going to be whatever's left. And so now all we have to do is just take our derivatives and integrals real quick. So x squared becomes 2x, becomes 2, becomes 0. And then cosine of x becomes integrated to sine is positive, integrated to cosine is negative, integrated to sine keeps it sine. Okay? And then all we have to do is go across and diagonal. Okay? So now we get x squared sine of x, and then minus and minus is plus, 2x cosine of x, and then we have a plus and a minus, so we get minus 2 sine of x. Ooh, I lost a 2 somewhere in this other one though. Yeah, here it is. I forgot to pull this 2 out. See? And here I am preaching about being careful. Okay, so we see how much faster the tabular method is, and honestly how much it prevents you from making mistakes. So I've seen it a couple different ways. I've either seen, the way I was taught was LIP TE, but I've also seen the P be replaced with an A. It's whatever you want. They mean the same thing, it's just a different way of saying it. So here we're going to have logarithm, inverse trig, polynomial, and then t is regular trig, and then e is exponent. Okay, so the way this works is the closer it is to the left, the more likely it is you want it to be your u, and the closer it is to the right, the more likely it is you want it to be the dv, your integral. And then this A stands for algebra, if you decide to use A instead of P. I never thought it made as much sense as Li8 doesn't make as much sense as LibT does, but whatever's easier for you, they both work. So in that last problem we had x squared and then sine of x. So we had a polynomial and a trig. So if we look at this, the closest to the u is the polynomial, right? So that's going to be our u, and then the closest to our dv was the trig. So that's our dv. So we followed our rule, which was really nice. Now there's times where it may be not so obvious what you're going to want to do. So if you have an integral, for example, like e to the x and sine of x, well, e to the x is an exponential, and sine of x is a trig. So in this case, we would say u is our trig, and dv is our exponential. But let's do the tabular method and look at that for a second. And I think most of us already kind of know how this is going to go. We're going to go in circles. So we get plus, minus, and I'll just do 6 lines. Okay, so if we're choosing the sine of x to be our u, and e to the x to be our dv, so our u is the derivative, so we get sine of x, derived as cosine, derived as negative sine, and then the sign stays the same, and the sign changes, and we see where this is going. And then integral of e to the x is just e to the x. So we can just write that a bunch of times. Okay? So this doesn't really seem like it's going anywhere, which is probably annoying. But we actually went somewhere really cool with this, which I'll be able to explain bootstrapping here while we're still waiting for our friend to get his question typed up. So if we notice, we did our derivative enough times for it to repeat with the same sign, but you can actually stop where it repeats with the opposite sign. So let's write out our integral up to this point. Now when you go straight across, you're going to add an integration sign, right? Because we're stopping at that step. So positive, positive, so we just get e to the x sine of x. And I'm going to write the whole thing. So I'm going to say integral of e to the x sine of x equals, and then we have e to the x sine of x, and then we're going to have negative e to the x cosine of x. And then we have this this negative here is the only one, because that is not a negative, it's just an arrow. Okay? So we have minus the integral of e to the x negative sine of x. Sorry. Okay, so negative ex sine x dx. Well, gee willikers, that looks really familiar. So this ex sine x, well, that's the exact same as this, just negative, but we know we can pull the negative out. So let's do that. So we're going to pull this negative out, so this becomes positive. Something's wonky. Oh, this is supposed to be positive, sorry. There we go. So pull the negative out, this becomes negative. And then, since this is the same as this, why don't I add it over? So now I have 2 integral of ex sine x is equal to ex sine x minus ex cosine x. Well, I still need the integral of this just by itself. So let's divide everything by 2. So now I know that the integral of e to the x sine of x is equal to e to the x sine of x minus e to the x cosine of x, all divided by 2. And so this technique was taught to me as something called bootstrapping. You can call it whatever you want, but basically when you have a cyclical integral, you just have to get to the point where it repeats, and then use a little bit of algebra to push it back over and isolate, right?